Good morning, good afternoon, and good evening, everyone. Thank you for joining us today, and welcome to the DAS RCN webinar on machine learning for DAS data analysis. I'm Casey Adderholt, speaking from the Incorporated Research Institutions for Seismology headquarters in Washington, D.C. IRIS is a consortium of universities and an NSF-funded science facility operating programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. This webinar will be recorded and archived on the IRIS Earthquake Science Presentations webinar YouTube channel. Should you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box, not the chat box, on your Zoom control panel. At the end, we will read your name and question to the presenters. If similar questions have been asked, we may combine or skip them. If the webinar happens to crash due to Zoom or internet issues, we will reboot it. Just click the webinar link again. Use of distributed acoustic sensing is rapidly expanding in our community, prompting the initiation of a research coordination network to facilitate workshops, tutorials, and other opportunities for sharing ideas and resources. This is one in a planned series of webinars on different topics within distributed acoustic sensing. Today, we will have 4 presenters, so I'm going to pass this to Bin Lu now to introduce our first speaker and get us started today. Bin?
Okay, thank you, Casey. So hello, everyone. Good morning, good afternoon, good evening, depending on where you are. I'm Bin Lu. I'm currently a postdoc at Stanford University, and I'm actively working on DAS data analysis. And it is my pleasure today to introduce our first speaker, Dr. Whitney Trainor-Guitton, to start this webinar on the topic of machine learning and DAS. So Whitney's main topic of research is quantifying value of information, aka VOI, which requires statistical measurements of geophysical data and models. She has achieved VOI values by blending spatial statistics, data science, and geophysical inversion techniques for a variety of problems, like geothermal exploration, groundwater remediation, and CO2 sequestration. And during her time at Livermore National Lab and Colorado School of Mines, she was involved with the Paratomo project for Bradley Hot Springs, working with both the vertical and horizontal DAS data. She also designed and installed the Kafka Commons DAS array on the campus of Colorado School of Mines. She recently joined Zanskar Geothermal and Minerals as a senior decision scientist. And the title of her talk today is going to be Machine Learning is Driving a Revolution in Seismic Listening for Geoscience. And please don't forget to type in your questions in the Q&A box and I will read them out for you. Okay, and here I'll pass it to you, Whitney. Take it away.
Thank you, Ben. Ben was one of the original founding members of our DAS machine learning working group. The others are listed here as well, including myself, Eileen, Veronica, Nicole, and Vincent. And so today I'll just be presenting some of the work we did as we were getting started as the DAS machine working group. And we kind of coined this little acronym of DAS plus ML to represent all the studies that represent the intersection of DAS observations with machine learning used as either a processing or interpretation technique. So again, this work is representing the kind of beginnings of us understanding the landscape of this work and what had been done before, and hopefully serves as a nice motivation for the rest of the speakers. So as Ben mentioned, my first experience with DAS was on the Paratomo project, which we thought was a deluge of data. We are now collecting very highly spatial, dense seismic observations over 8 kilometers of horizontal DAS plus a downhole observation for 4 weeks. But as Ben knows, now there's ambient recordings that go on for months at a time, and this is presenting a deluge of data for us geoscientists. But as you might have seen in previous RCN webinars, there's even more larger data sets that are observing the seafloor telecom fibers. And if you had caught the last month's engineering working group, you now see that there's high potential and exciting possibilities for instrumenting our infrastructure, such as our roads, in helping inform autonomous vehicles, and also giving us ideas of the infrastructure conditions and health. And so with all this data, we have to think about how are we going to utilize this data and make interpretations and improve decisions potentially. And so our group kind of did a back of the envelope, pretty crude calculation to represent how difficult it will be to do these kind of interpretations manually. So if you think about how 1 week of recording represents over 600,000 seconds of data, and you very optimistically say that you could make some interpretations in 30 seconds for a 120 second data chunk highlighted here, then perhaps we would then, if we do 30 seconds of interpretation for 5,000 of these chunks, which would be within 1 week of recording, that would be about 42 hours of interpretation. So you're looking at a whole work week of interpretation for 1 week of recording. And this is, again, maybe looking at about 2,500 sensors. But if we start considering city scale fiber and smart cities initiatives, it's going to be impossible. And so that's why naturally machine learning methods is a great fit with DAS data. It can help us more efficiently make these interpretations and also do some processing. And so again, the first work of our working group was to kind of look at what were some of the seminal papers in this area of DAS and machine learning. And Vincent made this really pretty chart of some of these studies. And from our, to the best of our knowledge during our literature review, we found that the first neural network was applied to fiber optics data in 2002 in order to help see different signatures in water from different pollutants. And then around 2013 is one of the more seminal DAS as applied to subsurface papers in the Daly et al. Leading edge article. And this didn't use machine learning, but it was one of the first to say that these communication fibers downhole could be used to interrogate the subsurface away from the well. Around 2015 is when we see classic machine learning techniques like support vector machine used in combination with DAS data in order to do perimeter monitoring. And then in 2017, deep learning, CNNs, were used to actually discriminate between different sources that were observed in the DAS data. And then lastly, in 2018, we see how an application of GANs in order to make very efficient labeled training data sets, which, as those of you in the audience know, that labeling can be the most onerous step in machine learning. And so in that realm of papers that are using both DAS and machine learning, we had about 33 since 2015. And you see that the majority of the applications for that was for tracking. So trying to see what types of sources were moving around a perimeter. And the rest you can see were infrastructure, health, noise removal, producing data, or microseismic and hydraulic fracturing. Two really useful review papers were Tejedor et al. In 2017, and most of those were using the more classical algorithms. And then after 2017 is when you really see, again, those deep learning methods being applied to the DAS data. And so, again, here's the breakdown of, from those 33 papers, what types of methods were used. And again, from this review, we saw that 20% of them were applied for subsurface characterization, which I assume many of us on the call know that subsurface has many unique challenges as opposed to maybe above ground applications. The first being labeling. We can't directly observe earthquakes or fractures opening in the ground, whereas the other above ground studies could actually make the observations of what were the sources of their noise or their signals, such as trucks or people walking excavators, etc. And so one way that this has been handled in the case of Microseismic is that there are 2 papers out that use the real DAS noise that was observed and combine that with physical modeling of microseismic in order to then have more confidence in their labels. Besides labeling challenges, most of the DAS studies for subsurface tend to have longer fibers, so that's going to create even higher volume of data. And also often we're collecting data in fields that might be remote and that can be far from data storage locations. We did find that fortunately during the development of DAS for geoscience, there was also concurrent developments in computing power, which definitely helped along the ability for machine learning to be applied to DAS data. But we do recognize there's still a great need and potential for ways of handling this data and reducing the kind of input-output load. So data lakes and edge computing are 2 possible solutions for that. On a whole, and the big takeaway is that we believe that machine learning provides a great solution to really move DAS from a research topic into kind of actionable, automated interpretations and decisions to be made from this data. And so to do that, there needs to be a lot of confidence in how these algorithms are working and the interpretations they're making. And so, of course, developments would need to be in accurate labeling, looking at what are some domain-specific feature in engineering, what are the characteristics that are needed for each problem. And some of the talks that you'll hear after me from Martijn and Eileen and Fantine will look at how machine learning can improve data quality and improve processing efficiency. And ultimately, we want to get at automated interpretation of events that are important for the subsurface and make better decisions regarding our groundwater resources or exploration of geothermal, and ultimately to help improve efficiency for our cities, again, for these smart city initiatives. I won't take any more time because we want to get to the exciting scientific talks for the rest of the webinar, but I just want to welcome anyone who's interested in being involved in our working group to shoot me or Eileen an email. We meet monthly, the 4th Thursday of every month, so we would love for you to join us.
Thank you, Winnie, for the great introduction about the purpose of our working group and start up this machine learning plus DAS discussion today. And for the audience, please type in your questions if you have any, and I'll read it now for you.
If there are no questions, and we can take them, I think, at the end too, I can go ahead and introduce Martijn and get going on his talk.
Yep, that could work. Or maybe we just wait a little bit more, see if there's any question coming in. I see one. Yeah, it's more general question from Sanjay. Where can we get the PowerPoint that was shared?
Well, I believe, I mean, the YouTube channel will have this. I'm not sure if we're able to post the slides anywhere on the RCN website. Maybe Casey can answer that.
Yeah, we'd be happy to post those if you're willing to share. And yes, the recording will be made available later on YouTube.
Thank you.
So I'll go ahead and introduce Martijn. Martijn is a postdoc at the Université Côte d'Azur in Nice, France, and he's funded by 3IA Côte d'Azur Institute for Artificial Intelligence. His current research involves integrating deep learning solutions into DAS signal processing workflows, such as beamforming and filtering. These hybrid tools are then applied to challenges associated with the theme of smart cities like traffic monitoring, railroad quality control, and urban geohazards. In this talk, Martijn will show a deep learning filtering technique that works especially well for DAS data and that can be applied to a range of seismological problems.
All right, well, thanks a lot, Whitney. So I would like to start with this picture of a zebra. And in my mind, a zebra is kind of a special animal, and that's because it is coherent. Now, what do I mean by coherence? Well, if I were to put a patch on top of the zebra so that I cannot see what is underneath, then I can still kind of guess or predict what the patterns will be underneath this patch A. Whereas if I look at the bushes on the ground, and if I were to put a patch on the ground there, then I cannot actually predict the details of what these bushes will look like. I can probably guess that it is green, but that is pretty much it. And the reason for this is that with the zebra, we have these stripes that you can follow and that you can basically interpolate across this patch. Whereas for the bushes, the details are only very locally coherent and do not extend to longer wavelengths. So we cannot really interpolate the details of these bushes. Now we can make this a bit more formal by using this concept of what's called J invariance. This was coined by Betts and Royer in their, I think it's an excellent ICML paper published in 2019. So suppose that we have some input Z for which we can define a partition. A J invariant function, G, is one for which the output does not depend on Z that is restricted to J for all Z and all partitions. Okay, this is a very abstract description, but if we bring it back to the zebra example, our input Z is just a picture of the zebra, so a collection of pixels, and J is just a patch of pixels that we select. And what I did before is I will try to predict these stripes on the zebra. So G, our function G, would just be a prediction of what is underneath that patch J. And as these authors that I mentioned above have shown, is that associated with this concept of J invariance, there are all sorts of very nice theoretical guarantees, like that it can actually lead to an optimal denoiser. So how can we use this in practice? Well, many of the signals that we record with DAS are coherent. They are coherent in space and in time, like for instance, this earthquake on the right, but also things like ocean waves or cars that are traveling along the fiber. So here on the right, what you see on the horizontal axis is time in seconds, and along the vertical axis, we have the distance along the fiber. And this cable recorded an earthquake, which you can see sort of on the right side of the picture. And the colors here indicate strain rate. But on top of our interesting earthquake, we also have lots of incoherent noise. And this incoherent noise may obscure some of the more faint signals of interest, like what you may see over here, for instance. And already these data that I show here are filtered in an earthquake frequency band. So the noise and our signal of interest occupy the same frequency band, and so we cannot separate them by traditional frequency domain filtering. But using this concept of J invariance, we can actually filter or separate the signal from the noise based on their coherence. So to demonstrate this, we will look at some data recorded in 2 DAS experiments. These experiments were conducted in April 2019 on 2 cables that were called HCMR and Nestor. So these cables have been deployed offshore Greece. So here's an overview map to see where we are. And during this experiment, several regional earthquakes were recorded. So for each of the earthquakes that we detected, we did some basic bandpass filtering between 1 and 10 hertz, downsampling to 50 hertz, and then cropping in a window of about 41 seconds around the first arrival. And so now we have a data set of earthquakes recorded by these 2 cables. And then what we did is we selected a set of 11 neighboring channels and took their waveforms. So here in this cartoon, I show only 5, but in reality, we selected 11 waveforms. And out of those waveforms, we set one of them to 0. So keep in mind, these are from neighboring channels. And so we put this set of waveforms into a convolutional neural network. And so the target for this neural network is to reconstruct that one waveform that we set to 0. Now, bringing this back to the example of the zebra, in a way, this is the same as putting a patch on an image, right? We're just hiding a little bit of the input to the model. And so the goal is now to predict that part that you cannot see, which is exactly the definition of J invariance that I discussed before. Now, in this way, we can reconstruct one waveform at a time, so from one channel at a time. So if we basically slide this model through our data, reconstructing one channel at a time, then we can essentially reconstruct the entire data set that we have. Okay, so here's an example. So here on the left, we have the original data that this bandpass filter is between 1 and 10 Hertz. Again, on the horizontal axis, we have time. On the vertical axis, we have the distance along the cable. And we can clearly see the earthquake after about 25 seconds over here. When we feed this into our neural network, we get this. So this is the output after reconstructing these channels one by one. And now we can see this earthquake very, very clearly. The noise that we were seeing just before the earthquake is basically all gone. And because of that, we can also see much more finer details that seem to be appearing before these very strong ground motions. So whereas in the previous, so in the original data, one might say that the first arrival would be around 25 seconds. But if we look in more detail after filtering, we can clearly see that there are some arrivals already happening at 15 seconds, and that these arrivals over here are most likely just surface waves and not body waves. Here is another example of a different earthquake. And again, it's the same picture, that by using this filtering technique, we can uncover these much more finer details and analyze them in much more detail. And if we look at some individual waveforms recorded along given positions along the cable, then we can see that, especially in the top and the bottom waveforms, that the noise is being, well, basically zeroed out essentially, and that the original earthquake waveforms, in this case the surface waves, are quite well preserved in terms of the amplitude and phase. Now, mention that this technique is based on coherence, and so you would expect that also we can improve the waveform coherence with this technique. And sure enough, if we look at one particular earthquake, so here on the inset we see a location of the earthquake that was recorded by the HMR cable. And if we measure the waveform coherence locally along the cable, then we can see that everywhere the waveform coherence increases by as much as 30%. And so this should be beneficial for coherence-based techniques such as beamforming and also template matching. So here's one example from if we do beamforming on this particular earthquake. So the way to read this diagram is along the circumference, we have the back azimuth of the source. So the true back azimuth is given here by the star. And along the radius, we have the apparent velocity that is inferred from the beamforming analysis. The colors here indicate the strength of the signal. And if we do this on the original data, then we can see, well, lots of essentially chaos happening here in our radar plot. Whereas if we apply the beamforming to our filter data, then we can clearly see the two most coherent signals in there, which is the direct arrival of the surface wave and also a scattered arrival, which is in the direction of the southeast. So just to wrap up, I just want to mention that this approach is entirely self-supervised. So we do not need to have a clean ground truth. We don't need to know what a clean signal looks like. It'll figure it out by itself. And also this model is relatively small in terms of the number of parameters. So it is fast to train and requires very little data. And we can now use this to also separate signal from noise that share the same frequency band. And also the signal coherence clearly improves, which will then help us to do more detailed and better coherence-based seismological analyses, such as beamforming and template matching. So if you're interested in trying to apply this for yourself, We recently submitted a paper describing this method, but the preprint is already available on Earth Archive. And also all the codes and data and pre-trained models are available on Figshare. And if you have any questions, you can also drop me a line either via email or Twitter. Thanks a lot.
Thank you, Martijn. We'll give people a chance to type in some questions. So we have one. How does this compare with Kalman filter-based techniques for this kind of data?
Common filter-based technique. Sorry, I'll just read the question myself. Kalman. Actually, I have not compared this with Kalman filtering. In the preprint, we compare this with some other more traditional image filtering techniques, non-local means and BM3D. And in comparison to those, our technique is, well, first of all, much faster, much more efficient, and it also preserves the finer details much better. But we haven't compared this with Kalman filtering.
The second question is, how is the cable direction determined?
As in the orientation of the cable, that we got from just the deployment reports. So they dragged the cable behind the boat to deploy it, and so they knew the GPS location of the boat. So that's how we sort of guess where the cable is, but it's not very exact though.
Third one, that's so clever, really cool. Do you think it loses or maybe gains some efficiency due to some averaging over the gauge length during acquisition?
No, I don't think so. So basically the gauge lengths give you an average strain or strain rates over that distance. And that's simply what we measure in terms of phase shift or shift rate. So yeah, so the raw signal is just what we have that comes from the DAS, and then this will just apply to any kind of DAS data that we get. Also, if the gauge length changes, you can simply retrain it a little bit on new data, and then it will work on also other gauge length or channel spacings.
Do you think it's possible to go beyond 10 Hertz, or does it become too noisy?
Yes, it's definitely possible, but that depends on the spectrum of the source that you're interested in. So I guess if you have, if you're looking at microseismicity and looking into higher frequencies, then yeah, I mean, if your source is powerful enough in those frequencies, then you can also extend it to higher frequencies.
Some types of noise are coherent. Can this technique help discover signals in such noise?
Yeah, so that is an interesting point, that we define noise as something that is incoherent, or at least it is only very locally coherent, that it doesn't extend beyond 1 or 2 gauges. So things that are strongly coherent, like for instance, ocean waves, yes, those will not be filtered out, and actually they will be more prominent in the data after you remove the incoherent noise. So yeah, so for this particular task, we defined noise as something that is incoherent. But Eileen actually has a very interesting approach, or she already published that some time ago, about using representation learning to getting the different kinds of noise and then extracting the or suppressing the coherent noise signals. Yeah.
There were some blind traces in your filtered example, which seemed not to be filled by the coherence analysis. What can you relate these blind traces to? Orientation of the cable or coupling of the fiber?
Like for instance, over here, we basically have these very large segments where we do not have much of an earthquake signal. This is probably due to coupling, which is very heterogeneous on the seafloor. And thankfully, those are not filled in with this technique. If we look at the filter data, we don't see any new signals being created, which is of course what we don't want, right? We do not want to create imaginary signals. So yeah, one very nice property of this model is that if there is nothing there, just noise, then it will not fill it in with something else, which you would maybe expect from denoising autoencoders, which have a maybe very strong prior, and that will impose that prior onto your data.
So we have 3 left, but I think we can get to those at the end. So why don't we move along to Eilen's chat talk?
All right, well, thanks everyone for the interesting questions. And then I think it's my turn to introduce Eileen. So let me just get my my notes. All right, so yeah, it's my great pleasure to introduce Dr. Eileen Martijn, who is an assistant professor at the Department of Mathematics and Division of Computational Modeling and Data Analytics at Virginia Tech, where she is a Luther and Alice Hamlet Junior Faculty Fellow. She received her PhD in computational mathematical engineering and a master's in geophysics in Stanford. Her research includes large-scale sensor network analysis, computational methods for environmental geophysics and geotechnical engineering, distributed acoustic sensing, passive seismic methods, and applied optimization. So Eileen, if you're ready, you can take it away.
Yeah, thanks, Martijn. And thanks for a really nice talk on especially that incoherent noise. So in this talk, I'll focus a bit more on noise exploration and detection in large-scale DAS data using machine learning, but really focused on when we have those coherent noises. So let's take a look at some examples of what some of these noises are. So especially in urban areas, we tend to get a lot of vehicles of different types. So here's an example from the team at Caltech that was looking at motorcycles and floats during a parade, or this array that was done by a team at Lawrence Berkeley Lab looking at an array in Sacramento where they were seeing vehicles from a farther distance. Here's an example from Penn State where we actually saw people walking. And here's some examples of a car driving by, or a busy road, or a construction pop. And those were all time and space domain representations of those. We can also look at what our noise is like in the frequency domain. And sometimes we see more subtle signals there. For instance, things that are these horizontal stripes in our spectra that are most likely things like heating and air conditioning systems. Or at Penn State, we saw something similar with signals from steam pump systems or steam tunnels. A lot of times we're trying to target that noise so that we can remove it and then focus on other signals that we're interested in. For instance, like in Martijn's talk, he was saying that he's interested in earthquakes. He wants to remove that noise, right? But sometimes we might actually be trying to target that noise so that we can use it as a source of energy. For example, there's a paper by Shandou in Scientific Reports where she really tried to target using cars as a source of energy for near surface imaging. But those vehicles can also cause problems for us when we're trying to do things like passive imaging. So one of the first times that I saw this issue come up where we had really strong artifacts was at the Fairbanks permafrost thaw test, which was led by Anna Wagner and Jonathan Aho Franklin at the Army Corps of Engineers and Lawrence Berkeley Lab. So here's an example of what that array looks like. So we've got a road here. It's got some rough patches marked in green and some road joints marked in red. And then over on the right, we've got our fiber optic array drawn in white here. And whenever we would have a car drive past the array, our data would have those rough patches show up and those strong bumps setting off near surface Rayleigh waves while the vehicle was passing. And those were really strong. When we would try to do ambient noise interferometry analysis to get some data that would look like active source data from our just ambient noise, we would mostly get what we wanted. So in pink here, I've marked the signal that we want to see, but we also got a bunch of artifacts marked in green here that looked like little crisscrossy copies of our noise correlation function or our wave equation Green's function that we wanted. So we needed to figure out how do we get rid of those artifacts. And we put a lot of energy into getting rid of those by trying to target those vehicles, trying to remove those vehicles. So I worked with Ethan Williams, who was an undergrad at the time, trying to get some car tracking tools. Nate Lindsay also came up with another sort of image tracking solution for this, and Shan Do came up with another heuristic for saying whether a window should be accepted or rejected based on whether there was a car there. It was a lot of human energy to just target this one problematic type of noise source, or this one noise source that we wanted to target. And so we didn't want to have every single noise that we came across as we went into different infrastructure situations or cities to be that much work. And so when we started looking at the Stanford DAS array and saw different types of noise sources there, we needed to find more unsupervised solutions to be able to detect and remove cars or other noise sources that we might encounter. So the Stanford DAS array ran for several years in this configuration where we had about 2.5 kilometers of fiber optic cable underground around campus. There were some areas that were near busy roads, like up here. There was a big construction site, another construction site down here for part of the time. And of course, lots of foot traffic in certain areas of campus. Here's a spectra of just 1 week of noise there. And you can see this strong day to night trend. We got a lot of anthropogenic noise there. Even seasonally, we would have some trends in our low, mid, and high frequency sounds or vibrations that we were recording. So when I was trying to do ambient noise interferometry to image the near surface there, these cars were a major issue for us. And so I teamed up with Martijn, who's going to give the next talk also, Yinbin Ma and Robert Suplicki, to come up with some tools to be able to remove those vehicles after detecting them. So ultimately what we came up with was taking small windows of the data, using continuous wavelet transforms of that, and then doing clustering of those continuous wavelet transform features. And the continuous wavelet transform is really nice in that we can take patches of data that include both space and time, and we can see when there's spatial coherency or certain move outs, either because of the velocity of the medium itself, or because of the velocity of moving sources, such as a vehicle, or had we been able to detect people walking, we would see that. On the right, you can see that we've plotted what is the frequency with which we're finding different sources within certain clusters. And there was one cluster that was really found a lot alongside a road, and every once in a while along some smaller roads that were less busy. And so we found that that was our vehicle cluster. And in fact, we were able to distinguish that other loud noises were ending up in another cluster. And so it wasn't just that that cluster was saying these are loud. It was saying that using those continuous wavelet transform features, we were actually seeing that we were getting those signals with certain move outs that were close to the vehicle velocities, all falling into that category. Ultimately, from my perspective, as someone doing ambient noise interferometry, removing those cars helped improve the convergence of our noise correlation functions, which gave us a usable signal much more quickly. And Martijn really dug into this even further, and she was able to improve the accuracy of this by using synthetic training data and also using neural networks instead of just simple k-means clustering. But this kind of workflow of using continuous wavelet transform or other simple features with clustering is a really useful way to start just going through a large amount of data to get a feel for what kinds of noises you're getting. And so I think this is an easy thing that anyone can do as you're getting into a new, really large DAS data set. More recently, at Penn State, the 4C array, which is about 5 kilometers long, with Tianju and Junju Shen, has had some very different types of noises than what we saw at the Stanford array. We've been able to get things like a concert recording, which actually tells us some interesting stuff about being able to detect airwaves with those buried sensors, which we were a little surprised by. And we've also detected footsteps. So for some reason, this array seems to be a little bit more sensitive in its pedestrian areas. And so up top, you see what the raw data looked like for just one window of data, just a few minutes. And down below, you see after bandpassing that data from 1 to 5 hertz. And Junju actually went out and did some experiments to really verify that, yes, indeed, these are people walking at between 1 and 2 meters per second, typically. But we don't want to see those footsteps. For one, they might mess up any ambient noise imaging that we want to do to understand the near surface in that urban area. But also, when we think about how DAS is growing and how especially DAS is growing in urban areas where there may be a mix of residential and commercial activity, we don't really want to be recording people's footsteps. It may make the community that we're recording data in uncomfortable with what we're trying to do scientifically. And so we wanted to come up with some tools to automate the detection and removal of those footsteps. And this actually seemed like a really good fit for an undergraduate project. So I worked with Srikant Jakanpudi, Wei-Chin Lee, and Ayush Dev, who were all CMDA undergrads here on their senior capstone project, to come up with a workflow that basically ended up being a simple computer vision problem. At first, we tried the k-means clustering of our data, similar to what was done at the Stanford array with vehicles, but it just didn't quite work out for this kind of more subtle signal of footsteps. So ultimately what we did was kind of bandpassing our data into this 1 to 5 hertz region that we thought was a useful frequency band, breaking it into small windows of about 30 seconds, and just a collection of maybe 100 or so channels at a time, using that as kind of an input, as an image input to a multi-layer convolutional neural network, which we optimized to have just these dimensions and activation functions, and ultimately just got a yes, no for every window of data. Are there footsteps in here or not? This way, we're able to go through every window of data automatically and say, if there are footsteps, we might remove that data, just mute it out, or we might remove it with some random probability, depending on what the right approach is for our data, for our problem. And we found that we were able to get about 84% accuracy with the supervised method. So the students actually put together a collection of more than 4,000 samples of labeled data, making sure that it was all balanced of footsteps and non-footsteps. And then this was just our test results with a little over 1,000 samples that we ran that on. And we see that, okay, a lot of times we're able to get it right, whether there are footsteps or not. Sometimes we don't quite get it right, especially if there are other loud signals in the area, or if there are weak signals where there really were footsteps that were very weak, but we didn't detect them. But it was only because we felt that these footsteps were such a high priority for making sure that people are able to take into consideration data privacy concerns that residents may have in an area, that we felt like it was worthwhile to really put in the effort to get that kind of a training data set that was labeled. As much as possible, when you're able to use things like semi-supervised learning or GAN to sort of speed up the creation of labeled data, that's definitely a preferred alternative. Looking forwards at what our community really needs for this kind of denoising exercise is, it would be great if we had a community webpage where people can put up examples of common noises and maybe any kind of characterization or description that they can have. This wouldn't require a lot of standardization. It may not be quite as useful as something that is standardized, but I think it would be really easy to get people to contribute to this and have a lot of value for other people who are working with DAS data and encountering noises in so much more detail than they ever have before. Additionally, there are a number of open DAS data sets, and the DAS RCN is going to be putting up a web page that includes links so that you can know where to go for those open DAS data sets, and hopefully that will help us with getting more common comparison of our machine learning methods. You know, an ideal case would really be to have a true repository with labels on our open data sets and have some kind of standardization of that metadata going with it. So hopefully in the future, we're able to sort of move towards that as a community. But the takeaway message from this is that the spatial density of DAS makes it possible to really distinguish your local noise sources and to see those in a lot of detail, but it's extremely time consuming to manually identify and design denoising filters for every type of noise that we'll encounter. So sometimes unsupervised learning can provide tools to help us do that kind of initial exploration and target certain noise sources. But if we have really high priority noise sources, we're often able to better target those using supervised learning, but it does require quite a bit of effort. So here's some acknowledgements on those experiments and collaborators on those. Thanks.
Thanks, Aline. It was a very, very nice overview of basically everything that makes noise. I haven't seen any questions yet in the question and answer panel, but if you have any questions, please put them up now. All right, I see one coming in. So Joseph is asking, interesting presentation. Wondering why the CNN used a softmax activation in final layer when you're performing a binary classification.
Yeah, that's a great question. So for this one, I think that if I remember right on what the students had done on this, ultimately they decided that they would just sort of cut off the results there. So they tried out a few different functions there and then just did a comparison on which one would reduce their test error. So I don't have a great answer for that, but yeah.
All right, then let's see if there are any other questions in the meantime. If not, then I'll ask a question in the meantime. So do you think that the accuracy of this method is just a matter of increasing your data size? Did it level off the performance already? Or do you think you can squeeze more performance out of it by just increasing your data set?
Yeah. So I think that increasing the data set beyond 4,000 or 5,000 samples, I don't know that in this example, it will actually have a huge impact. I think that the bigger thing that could have more impact in this particular application would be that there are actually some windows where there were some small mistakes and things. So sometimes in the corners of windows, there may be footsteps that were labeled as not being there. And so there are some of those things where there are actually inaccuracies in the labels. And so focusing more on that issue of inaccuracies in the labels might be a little bit better for this particular problem, just to sort of clean up the data set that's already there with a little bit more time.
Right, then I see that in the meantime, Ray has a question. Seems as if this could be reversed to detect particular type of events such as earthquakes. So I guess Ray is referring to the fact that instead of focusing on the noise, you can focus on the signal that you're actually interested in.
Yeah, that's a good point. So actually I'm working with Julius Grimm over at ETH Zurich, who's a student there on doing icequake detection, and many of the methods that we're trying to use for detecting icequakes are very similar to, and if you don't know, icequakes are basically earthquakes, but on a glacier. And so the methods that we're developing there are very similar to the methods for detecting certain types of noises. Yeah.
All right. Are there any other questions? I don't see them yet. Let's give people a moment to just type it up.
Okay. I'll just make a quick comment that next month's webinar will be a discussion on DAS data. So some of these points that Eileen was bringing up, and especially at the end of the talk there, will be discussed in more detail. So make sure you sign up for that when we announce it.
Excellent. All right. I don't see any more questions coming in, so I think we can move on to Fantine. So Eileen, I think you're the...
Yeah, I'll go ahead and introduce Fantine. Thanks. So Fantine Yu is a PhD candidate in geophysics at Stanford University. She's working on research at the intersection of deep learning and seismology. She received her MS in Science and Executive Engineering from the École Nationale Supérieure des Mines de Paris. And prior to her PhD, she was actually working as a software project manager on embedded devices. Her current research involves machine learning-driven event detection on continuous data, with applications such as traffic monitoring, earthquake detection, and tectonic tremor detection. So take it away, Fantine.
Having a couple technical difficulties there.
Yeah.
Okay.
Does that work?
I think
Okay.
I can hear you now. I think we just need to see your screen. So if you can.
All right. Give me 1 second. I'll bring that right up.
No worries. All right. Yep.
Oh, yeah. Can you confirm you see my slides?
Yes. Looks great.
All right. Thanks a lot. Yeah. So thanks for this introduction. And what I'll share today is some work we did on machine learning for microseismic event detection and how we sort of incorporated that into a bigger workflow of microseismic analysis. So this was very much a group effort. So work conducted with Ariel, Paige, Ben, Bob, Yondo, all at Stanford University, but also Thomas and Kurt at the Chevron Technical Center. And before we go into the depth of why we're interested in this microseismic event detection, really the motivation behind it is for microseismic analysis. And so microseismic analysis is now one of the main tools for fracture characterization in unconventional reservoirs. And in particular, it's really valuable if it can be conducted in time to influence stimulation and production engineering decisions. And as we have DAS fiber technologies of developing, we can now have these fibers deployed in the wells that are in the target reservoir. And that means that they're closer to the origin of where these microseismic events happen. And that means that they actually, by being close to to where microseismic events originate, we can pick up more microseismic events than ever with these DAS fibers installed inside wells. But as Whitney told us, well, this really raises a sort of problem of how we're going to tackle this microseismic event detection problem. Because, well, manual picking is time consuming. Nobody really wants to be doing it. But on the flip side, these DAS acquisitions, we're now recording continuously over time, and on modern systems, DAS fibers in your wells, they're acquiring more than 10 terabytes per day. And so you have no chance of actually shifting through all that data manually. On top of that, they often have low signal to noise ratio if you look at channel per channel. So it sort of makes this detection problem kind of challenging. And so what we'll do in this talk, we'll train a convolutional neural network for this microseismic event detection on DAS fiber. So a few words about the acquisition. So all the data I'll show today come from this unconventional shale reservoir. And so in this reservoir, we have 3 wells, and the sort of horizontal portions of the well, we have the middle well that is equipped with DAS fiber. And on the north and the south side of this fiber, around 215 meters away from the middle well, we have 2 offset wells. And these 2 offset wells, they're stimulated and perforated in what they call a zipper frac schedule, so an alternating schedule, one side to the other. And this stimulation activity is what generates these microseismic events that are then in turn recorded by the middle well. So if we have a little look at what these events look like, here we have an example of a manually picked microseismic event. So this one is pretty clear in the data. On the x-axis, we have the distance along the fiber, vertical axis is time. And we look at different events, we will see that the amplitudes can vary quite a lot among different microseismic events, and their focal mechanism is also different. So because of this task of microseismic event detection is not very well suited for, say, a thresholding-based detection, or even, for instance, template matching that wouldn't work with different focal mechanisms, or you'd have to have many, many templates. So what we did here is we started by creating a labeled data set of microseismic events. We created this curated data catalog, and we manually picked over 6,000 microseismic events on this DAS data. So what we did, we picked them over 2 stages of perforation, one from each side of the well, and then we randomly picked noise at random times and random channels, but at the sort of quiet times of the files that we had analyzed. And if we look at what the catalog looks like for one of these stages, so this is an event density catalog, and these are manually picked events. And every line is 5 minutes of data. This is one stage, so about an hour of data. And every pink dot is the event density for 1 second. It's the number of events, microseismic events, that we manually picked during that second. So we still see that the number of events per second is actually quite high. It varies between 0 and maybe 10. And we see that over the course of the stage, the number of microseismic events ramps up and then slowly tapers down again. And from there, what we'll do is we'll frame this machine learning task as a binary classification on windows that contain microseismic events and windows that contain only noise. And then we'll split our manually created data set, like carefully crafted data set, between a training set, which we'll use to train the machine learning algorithm, evaluation set, which we'll use for tuning the network architecture and the hyperparameters, and then a test set that is unseen data that we keep aside until the end when we'll test it sort of as a benchmark. And for the machine learning classifier, we developed this sort of modular neural network architecture. So this convolutional neural network, we wanted it to derive heuristics from state-of-the-art classifiers. So we sort of took inspiration from two networks, one's VGG and one is ResNet, which are sort of state-of-the-art for image classification. And but at the same time, we'll allow to sort of adapt this structure to our data. So we'll control the structure of the architecture with a number of hyperparameters. So we like had the number of layers or the number of convolutional blocks, a number of filters or what type of activation to use. And so we'll put all these sort of network design elements into the hyperparameter search. And this allows us to get sort of frame this problem as a compromise between exploration of network architectures that might perform well and exploitation of architectures that we know have proven to be successful at image classification. And after hyperparameter tuning, this is the network architecture that we obtained. And it's actually fairly small. It's a VGG-inspired network. It has 5 convolutional blocks, which is actually smaller than the official VGG network. But then when we think about it, our data set is also significantly smaller. And like these state-of-the-art classifiers, they're trained on data sets that have millions of examples and thousands of classes, and we have 10,000 and 2 classes, noise, and events. So it also makes sense that maybe smaller networks can tackle this task. And so we applied this, our best performing neural network on the benchmark test data set. We obtained an accuracy of over 98%, which we're really happy with. And also it had really high precision and high recall. High precision is good, which means that there's very few false positives. And high recall is also good because it means that we're missing very few of the actual microseismic events. So we then ran this on the continuous data. And we run it over the continuous data by independently flagging every sliding window over the data. And for every sliding window, we categorize it as events or not events. So this is our manually picked catalog. And we compare it with our machine learning detections. We see that it has remarkably the same trend. There's some differences, but so captured this ramping up and tapering down of the event density over the course of the stage. Some differences as well. We see that at 230, the event density really caps out. And that's really a limitation of how we have written this, how we've implemented our workflow, is because it's limited by the size of our detection window, given that the machine learning classifier detects windows as event or non-events, but the detection window is 0.25 seconds long. So if there's multiple events happening within a window, it cannot separate between these events. So it's basically capped out by the detection capabilities caps out because of the sliding window size. Another observation we made is that we turned out to have some false positives. And so when we looked a little bit closer at these false positives, we were like, well, this doesn't look like a microseismic event. But then we performed 2-dimensional continuous waveform analysis over these false positives, over many ray parameters or many frequency bands. And what turns out is that actually these had coherent energy. And these turned out to be actual microseismic events that we missed during our manual picking. So we then scaled this workflow from our trained data set, from our created data set to continuous data over full stages that we did not label. And we did this over 10 different stages of continuous data. So a result of more than 20 hours of continuous data. And here we have, for all these detections, so after location procedure. So after running our machine learning algorithm over our 20 hours of continuous data, or our 10 different stages of stimulation, we found more than 100,000 microseismic events. We then, for each of these events, applied a location procedure to try to locate the apex. And once we had the apex, try to locate them within the reservoir. And that's hard to do because we only have one DAS fiber. But by constraining the events that had guided waves, which means they were in the reservoir, we could constrain the location to sort of the 2D plane where the reservoir is located. And so we derived the location from these kinematic properties of the events. And we plotted them again on the map. And when we made this plot, well, we thought it was really cool because here we have every stage plotted in a different color. And what we see is that they sort of represent this, there's a clear fracture direction, like the direction of propagation on this plot. And this direction of propagation even turned out to be very consistent across stages. And it's even different for the northern well and the southern well. So for the northern well, we see that it actually has a real propagation direction both away and towards the fiber. And for the southern well, we see that this propagation direction is mostly towards the fiber. So by having this sort of large number of events, we have really managed to create a mapping that's detailed enough that we start seeing this like clear trend popping up. And yeah, sort of to wrap this up, we performed microseismic event detection with an accuracy and efficiency far greater than with manual labeling. We would not have been able to scale this over so many stages if we had done it by hand. But in order to do so, we created this curated data catalog of more than 6,000 manually baked microseismic events. We then scaled our workflow over 10 stages, detected more than 100,000 events, and then performed a location procedure for all these events to really reveal this fracture growth location over these two wells. And I would like to thank Chevron Technical Center very much for providing us with the data and also allowing us to share these results with you. And I hope you enjoyed this talk.
Thanks very much for a nice talk, Martijn. As a reminder, please do type any questions that you have into that Q&A box. I do see, okay, so there's, well, I have a quick question on, earlier you were showing how with the events that had been missed in the manual process, you were showing this coherency of the events. And so do you see any like in that, can you elaborate a bit more on what it was that you're actually showing in the plot as far as like what that energy is that's coherent? Was it just amplitudes or a certain frequency band?
This one.
Yeah, yeah.
Yep. Yeah, I went really fast, but this is one plot among many. So this is the result of applying a 2D continuous wavelet transform to the data. And so the way we proceeded is that it's like a wavelet decomposition. We decompose the data redundantly over many, many different types of wavelets. And so as we're rotating these wavelets, so trying different rate parameters and also trying different frequencies of this analyzing wavelet, we have different sort of coefficient results. And so this is the absolute amplitude of the, like one of these continuous wavelet transform results. So this is for a Morley wavelet that actually comes down vertically on this plot.
Would there be a, like, do you think if you were to have been working with this form of the data to start with, would you have been able to use a simpler neural network, or does it take too much trial and error on the different types of wavelets and scales?
That's actually a very good, like, because this seems to suggest that we could probably use continuous wavelet transform as like a feature representation for machine learning. So we could have done the pre-processing. This would not have been very memory efficient. Like we already have terabytes of data, and like when you do this continuous wavelet transform, you're creating duplicates of your data. So you have to imagine that from a problem where we're trying to have less data, we're actually making more data. So it's, and the other thing is, I tried this experiment of trading off a convolutional neural network versus CWT wavelets on different data sets. And it turns out that what the CNN learns really is some form of wavelet analysis. So you don't per se gain that much by trading off. What you gain is more like in terms of interpretability, like you know which wavelets were important, so you can double check. But I think in terms of performance, you don't per se gain that much.
Okay, thanks. I see a question in the chat. It says, excellent presentation. Do you have a sense of the magnitudes that you can detect, or any sense of the magnitudes on the false positives?
That's an excellent question, because to have a good estimate of the magnitude, we would have to be able to locate it precisely for starters. And when it's really weak, we can't, like, it's hard to locate very weak events if you only have one fiber. So we can make an approximate magnitude, or maybe a proxy for the magnitude, sort of overall amplitude in the plot, but a precise estimate of magnitude would be hard to obtain. But I'm working on making a magnitude completion plot for this project. So we'll see what that yields.
Nice. I see one other question that says, DAS can't distinguish between events located on one side or the other because it's single component. So did you constrain the locations based on which side the stimulation was occurring?
Yes, that's an excellent catch. I went fast and glossed over it, but there is a lot of solving. Like, we can't resolve the cylindrical symmetry around the DAS fiber. So we did part of it by knowing that these events had guided waves, which means they were trapped within the reservoir. So it means they originated within the reservoir. And because we know the reservoir was skinny at that location, we constrained it to this 2D plane. And then to know on which side of the fiber it was, then yes, it's this. We picked the side with the stimulation.
Great, thanks. Here's another one that says, thanks for the talk. Do you have any comments on the number of data sets used for training? You use 6,000 events. Can we decrease the number?
Yeah, so we played with decreasing the number of these events because we went through the labor of picking these, and we don't want to go through the labor of picking these more than once. And we sort of wondered, like, when could we have stopped? And so we tried decimating this data set. And it really depends on what your end goal is. Our accuracy sort of went down a little bit as we used less events to train this neural network. So you'd have to imagine that we were at more than 98, and we sort of went down to 94, or with 300 events, I think we were at 94% accuracy. So 94% accuracy might sound good, but it also means that when you do your predictions on continuous data, your number of errors will increase. So you have to accept that you'll have more errors popping up once you run this over continuous data. Like if every one of your continuous, every 20th of your continuous windows reports an error, that might start becoming a lot of data to deal with. So it really depends on what your end application is. Like if your end application can handle a little bit of false classifications, then that would absolutely work.
Thanks. Here's another question that says, if you have more than one cable, might you be able to reject false positives on one cable and not the other with the trained network?
Check false positives on one cable and not the other.
I guess that they're asking about, can you analyze the data set just as it was recorded on one cable, perhaps?
And then test it on the other cables? I'm not sure if really understand this question, but I think 2 fibers is better than 1. So I think your results, your accuracy will improve if you get 2 fibers instead of 1.
Okay, and I'll just ask this person to type some more details. We're going to have an open question session in a second. So if you want to
please elaborate in the open
do.
Question. I'll be happy to answer.
Yeah, and actually, I guess I'll check with Casey. Should we move to the full open question at this point?
I think that's this is a good time to do that.
There's still several others though in the chat, so yeah.
Yep, so I think Fantine, you can stop sharing and we'll just have some time for open discussion. I think, yeah, Ariel had a comment to make, and so I think I enabled him to talk if he would like to.
Oh yeah, I just want to say that the location procedure is indeed kind of semi-counterintuitive. So, and Fontaine didn't have time to talk about it. So hopefully at the SCG, I will explain how it works and why it works, because you have a waveguide. Otherwise, indeed, it's a completely circular symmetry problem and you cannot resolve the location. So that was a very true comment by Cliff.
I guess we can just keep going with the questions that are already here, and then inviting others to also ask more general questions. Or
It looks like there's one for Fontaine and Martijn at the very end.
I see. So yeah, the question is, would denoising risk missing these false positives? Computationally, the decision would be that it would be what is cheaper, to denoise and detect, or to look at everything. So if we would, let's say that we would apply this this J-invariant denoising approach, then if these signals are really coherent, then they should pop up more. And actually in the preprint, we also show on synthetics that this method could potentially uncover or reveal signals that are way below the noise level, as long as they are coherent. So this would be great for microseismic events. Like Fontaine also showed, there is this very faint but still coherent signal in there, and that may be lifted out of the noise, and then it's a much easier problem to solve with the detector. So yeah, I see that there is some application of this denoising. On the other hand, if your network is not well trained enough, I'm talking about the J-invariant denoiser, if it's not well trained enough, there is a risk that it will just erase all of that coherent information because it's simply too faint. And yes, then you will lose it entirely, and then there's nothing left to detect. So this is more of a trade-off of how well can you train your denoiser before you move on to the detector. And I guess it's something that we can test with synthetics and such. But yeah, good question.
I think to some extent, it's also a function of your engineering problem. As in, if you don't mind, if your denoising doesn't computationally cost you much, you can run it anyway. If you don't mind losing some of these false positives, for instance, for microseismic analysis, we do not need every single microseismic event. We can afford to miss some. So I think it's very much a decision that depends on the problem you're trying to tackle.
So it looks like there's someone with their hand up, so I'm going to go ahead and allow them to talk and answer, ask their question. So Christopher.
Yes, hello. Thank you for giving me the opportunity to ask. I was just following up. I enjoyed the talk of Fontaine very much, and I'm following up on the comment of Ariel. I was wondering if your machine learning picks the arrival phases, and for the location, as Ariel implied, you need different phase arrival times to locate. And so I was wondering if your machine learning only discriminates between the time window has an event or has no event, or if it really yields the phase arrival.
So it's interesting. That's a very good question. And we wondered the same thing, because the way we set this up was, we said if the event window contains event or no events, because this is the most straightforward way of defining our classifier. But it turns out that if you look at the layer before the classification, sort of what we call these activations at the output of the neural network, you'll have strong activations weights really where the apex of the event was. So you could sort of retro engineer the apex of the event. The reason we did not do it is because we were interested in finding the apex of these events for the location procedure. And it turned out by just making basic assumptions about the kinematics allowed us to find the apex in a non-machine learning way, but just signal processing. So there was no need to sort of train a network specifically for picking the phases.
Right, so I see that David Hill has an interesting question. If any of these machine learning techniques can be implemented in real time rather than for post-processing. And so we've been thinking about also applying this J-invariant filtering technique in real time. That may, for instance, help detection for instance, earthquake early warning. Especially things like body waves may not be very easily visible on submarine DAS. And so, yeah, you really want to increase your signal to noise ratio. So currently, the model is based on convolutions. And so, well, these can be made to work in real time after some tricks. Also, for processing about 40 seconds of data, it only takes less than a second to do this, or to process that data set. So it is very fast. The problem is that you still need to pre-process the data a little bit by bandpass filtering, normalizing. Maybe if you are working with a seismometer array, you may have to remove the instrument response. So things like that may also, well, they also have to be factored into the total duration that you need to process these data. But I can imagine that, for instance, if there is a detection made with DAS, that detection then goes into a J-invariant denoiser to reevaluate that detection. And so in a way, it doesn't really work real time for the full data set, but it can be used to sort of as a, well, to double check your detections if there are any made. Maybe Fantine, if you have any other comments on like maybe if your algorithm can be used in real time?
Yeah, so we tried to design the problem by we obviously did it all in post-processing because we received the data as a full entity, and then we don't get to do it in real time. I think this was acquired in 2015, so very much not in real time. But we did try to design the whole workflow with a mindset of real-time processing. And this is why we're interested in this sort of smaller neural network for tackling the problem. And like we do think that once you have a pre-trained neural network, we've been experimenting with sort of decimating the training sets and things like that. So we do think that if you have even a small amount of microseismic events, maybe only 200 or 300, you can already get a pretty good accuracy with this type of sort of smaller network. And that would definitely work in sort of real-time predictions. And this is also why we sort of favor this approach over the sort of more sort of exhaustive approach of computing two-dimensional convolutional CWT, continuous wavelet transforms over the data, and then using that as feature space, because that would be computationally very memory intensive and would take a lot of amount of time and would not be able to be done in real time.
One of the things that's really held back a lot of people from doing those real-time analyses is also just that the interrogator units themselves and the software that comes with those prevents you from being able to actually operate the data in memory as it's collected. Instead, many of those actually lock you into a software system where you collect the data, it must be saved to files, and then you can start to process the data in the files afterwards. But there's all that wasted lag time in there. And there are a couple of smaller companies that have started to allow people to actually directly take those data streams, calculate other data products or features if that's what you want, while you're collecting the data, basically to set up those more kinds of real-time processing if that's what you think you want. I think a lot of us working in the research mode though are still, we'll try to do some of those so that we can have quality control more easily, so that we can start to scan through the data to do more machine learning analysis on data products instead of the raw data initially. But we'll still be collecting the raw data. And for a lot of research projects where you really do need that raw data to analyze, we're still going to not always be working in real time, I think. But that's definitely been an advance recently, like being able to work with those data streams that could make a big difference. I know Jonathan Aho Franklin and his group over at Rice are working a lot more on the edge computing that has more of that real-time aspect to it. And I see there's kind of a related question here that asks, when performing the data analysis in real time on the interrogator, do you have access to GPU computation capabilities, or are you needing to run your networks on CPU? And so for those interrogators where you're able to have access to those data streams that you can create as you're collecting it, I think that those do have at least one of them I know has a GPU. I'm not sure about the other one. It's kind of manufacturer specific what hardware they're putting into that computer that's actually collecting it. Of course, you can always have a setup where the data that you save onto files can be connected to any other computer, and then it's just whether you have a GPU on there or not.
So I see that.
Oh,
sorry, go ahead, Vincent.
On the GPU and I think GPU really helps for training your machine learning algorithm, but the inference part or the detection part of it can definitely be run on a CPU in a perfectly tractable amount of time.
Yes, I see that in the chat. Herb Wang also had a question in general, whether or not we foresee DAS toolboxes for applying different machine learning techniques, either for noise or signal enhancement. So with the our machine learning RCN, we are sort of collecting, or we have a GitHub where we now try to collect some software repositories for related to machine learning, but also DAS in general. So I'm not sure. Maybe Aline, if you can put a link in the chat, then people that are interested can just follow this repository to see, when we upload or fork anything that will appear on that repository. So also the J-invariant filtering work, after review it, I will try to make it more of a product so that people can use it out of the box and retrain it if needed. So that will definitely appear in that repository.
Yeah, I've just put the link to our GitHub organization. That's the DAS RCN. And so we've just got a little bit of stuff up there. I know there are several RCN members who are putting repositories up there. So, yeah.
All right, it looks like we have another question from the audience. I think it's Nima, if you would like to unmute and ask your question. If not, we can also proceed with any of the others in the Q&A.
Yeah, so there is a specific question about soil liquefaction from Wajahat. If the fiber was to be deployed vertically into the ground, would it work for soil liquefaction? I'm not sure what really is the defining feature of soil liquefaction, but with DAS you can generally measure any kind of ground vibration or just strain in the subsurface. So yes, with DAS I guess you can record all sorts of things. If it's coinciding with also for instance, the surface waves of earthquakes, then you have lots of signals appearing at the same time. So separating those may be a bit difficult, but maybe Eileen, maybe you have more of a background in soil liquefaction.
So I think that if I remember right, Ariel Lelouch, when he was looking, and maybe Sue Yuan, when they were looking at the fiber optic data that was collected along the SAFOD, San Andreas Fault experiment, I think that they analyzed some surface waves and they were looking at depth at like different levels of that. And so that might be the most straightforward way to look at liquefaction. There are other things. We've done things like VS30 estimation just for liquefaction hazard analysis as kind of a, in different spots laterally, what's that approximate VS30? But that's been, I think, the extent of what's out there. I don't know, Ariel, if you can maybe type into the chat or make a comment on if there's a reference that people should look at for that.
Yeah, so thanks very much for the assist, but I never did that. I mean, I was planning to.
This was your moment to take some credit, man.
Yeah, sure. Yeah, it works. No, I'm joking. No, I think you would need I mean, it's hard to see which phase is the surface wave because, yeah, I mean, you can see something that decays with depth, but you don't. It's hard to say if it's a surface wave or it's just some energy closer to the surface. But it is on my to-do list, so hopefully someday.
Oh, I thought someone had looked at this, so now I got to figure out who it was. But thanks, Ariel.
Sure.
Sorry to put
Thank
you on the spot. Oh, and I see a comment by Andres Chavaria that the British Geological Survey with OptiSense did some work on surface wave dispersion with, I guess, with vertical dust. So thanks for that comment.
All right, we can probably maybe wrap up this webinar unless there's any burning comments from any of the panelists that you'd like to say. There's some really exciting work happening here, so looking forward to it. All right, so thank you to all of our speakers today. The recording of this webinar will be made available on the IRIS Earthquake Science webinar playlist. If you are interested in future webinars, please join the DAS mailing list and check out the DAS website. I'm going to just post that in here really quick there. And thank you so much for joining us today.